going to look at these two functions, f of x and g of x, and figure out if these functions are continuous or not. Let's focus on f of x first. We can see that each piece of this function in and of itself is a polynomial. So the only place at which we could have a discontinuity is where we break. And at this case, where we break is 4. So we're going to test out if this function is continuous or not at an x value of 4. I've already set this up. I've already wrote down the limit as x approaches 4 from the left, the limit as x approaches 4 from the right of the function, and then plugging in the value of 4 into the function. As you approach from the left, your values are not going to be equal to 4, so you use the 2x plus 5. So 2 times 4 plus 5, and you get a 13. As you approach from the right, your x values are not going to be equal to 4, so you also use 2x plus 5. So you can see in this case, we get a little bit excited. The limit overall exists. And by limit overall, I mean limit from either direction. And is equal to 13. So let me write that down. The limit as x approaches 4 from either direction exists and is equal to 13. However, when you plug in 4, you have to use, since x is equal to 4, the bottom equation. So you get negative 4 plus 2, and that's equal to negative 2. So this is a discontinuity. The limit exists, but it's not the same as the function's output at the value of 4. And so we're discontinuous at 4 or at x equals 4. And that means our function is continuous everywhere else, from negative infinity up to 4, and then picking back up. You can use the union symbol if you feel comfortable doing that, picking back up after 4 all the way to positive infinity. Let's take a look at g of x, polynomials defined everywhere except for we have this thing happening at 3. So let's take a look at the limit as x approaches 3 from the left of our function g of x. Let's take a look at the limit as x approaches 3 from the right of g of x. And then let's look at what you get when you plug in 3 into the function g of x. So let's start with approaching 3 from the left. We're going to have to use this top part because x values are all going to be smaller than 3. And if you go 3 squared minus 4 times 3, you get out a negative 3. Notice that's what you're going to have to utilize when you plug in 3 as well, since the equality sign is in this upper part. So you're going to get a negative 3 when you plug in 3 as well. Well, what's going to happen as you approach 3 from the right? Since you're approaching 3 from the right, you're going to use negative x, which is going to give you negative 3. So what's that mean? That means our function is continuous at x equals 3. Now, that was the only problem we actually foresaw. So the limit exists. The limit is equal to -3. And the limit is the same as what we get as our output when we plug in the number. So we're continuous at 3, but moreover, we're actually continuous on the interval from -infinity all the way to +infinity. Okay, so we don't have to break it up. We're continuous everywhere. That is the end of section 1.5.